Now we're going to discuss multiple logistic regression. Basically the same thing as linear regression, multiple linear regression, the difference being that the dependent variable is binary. In this case, we're going to recall the Chow study, and in this study, there were two types of lenses, spherical and aspherical. And the aspherical lenses did pretty well. They're the open circles. The line that goes here is the black line is the line of identity. This is a baseline. This is a 5-year follow-up. You can see that pretty consistently the aspherical lenses grew a little bit, but not too much. Then the little black dots represent the spherical lenses that worked pretty well. And they worked about the same as the aspherical lenses. But then you have this group of spherical lenses that really did not do too well. The axial length just kept growing, even though they were all under ortho K for 5 years. Now the question is, why was that? And so we're going to make this our example for logistic regression. And let's look at our model. Now we have lens type 2, we have spherical works well, we have spherical doesn't work well, and we have aspheric. Well, we need to get rid of the aspheric lens because we just want a binary, and that's 3. So we're going to select cases if lens type 2 is it turns out the aspheric is 2, so we don't want any lens that is equal to 2. So okay, now you can see there's dashes through all the aspheric, but not through the others. Now works well is 0, doesn't work well is 1. So when we do this, we just have to keep that in mind, what these stand for. Now let's go to analyze, and just like in the logistic regression with a single variable, we go to binary logistic, and we're going to go to lens type 2 because now it just has those two values, 0 and 1. And we're going to see what are the factors that predict that. And so we have sphere, cylinder, I think I don't want to use cylinder because there's a lot of missing data. When you have missing data, it knocks out the whole subject. So that's not very good. We don't want sphere and axis. We'll do KT horizontal and vertical. Again, well, axis may be okay in this one, but I think we'll just skip it. The eccentricity, the E value, how round is the eye? Pupil size, how big is the pupil? Central corneal thickness. And we should also put in axial length at baseline, because this is the effect. So everybody is basically set to be equal at the beginning. And then we look to see if there are, well, no, I take that back. We want to adjust for baseline axial length, but we want to see which of these factors is likely to predict which factor was good at predicting which lens they were. So it's kind of a little bit of a backwards regression equation, because we say, okay, we have these variables, and now we're going to use them to predict whether or not the spherical lens would work or not. I guess that's not backwards. So here we go. So let's look and see. This categorical one is asking, are any of these variables categorical? Because like if we were doing analysis of variance and had groups, we would have that fixed factor plus the covariance for continuous. We don't have any of those here. We can save our predicted probabilities again. That'd be fine. Save us from doing that equation. Under options, we can do, I don't believe Homer or Lemma will work in multiple regression. We'll type that just to see, but yeah, I don't quite understand how it could. Because it's breaking down a single x value and we have multiple x's. Let's see, anything else? It doesn't look like it. So let's continue. And I don't know what style is. I'm not going to worry about that right now. Okay, so we have our multiple regression. We have a bunch of independent variables, our dependent variable binary. Let's see what we get. All right. So we have 191 cases. Nobody's missing. Now, works well is 0, so doesn't work is 1. So higher coefficients are going to mean that's predictive of doesn't work. I think that's an important feature you have to keep in mind. So when we look at our coefficients down here, oh, it did it based on expected. Okay. When we look at our coefficients, these are variables that are in the equation. The higher the b, the more it did not fit. So the higher the spherical equivalence, well, and then let's look for significance here. We have KT horizontal. So the higher your horizontal keratometry, which I think means well, I'm not sure. So anyway, if you have a high horizontal KT horizontal number, you're more likely to be a good fit. Notice that's positive, but it's not significant. What do we know about these two? They're probably highly correlated with each other. So we are the horizontal one in this particular situation of variables is winning all the variance, and this is stealing it from the vertical. So vertical was not significant. If we dropped horizontal, we would probably get a negative value with vertical. The E value, so the closer to 0, which goes from 0 to 1, E value goes from 0 to 1, so the closer to 0, the more likely you are to fit well. Pupil size, the bigger your pupil size, the less likely you are to not fit well, but to stop myopic progression. So large pupil size, bad. E value near 0, good. High horizontal, good. That's not significant. Axial length. The longer the axial length at baseline, good. Good progression. Good control of progression. All right. Now I want to, and we can look at, now the thing with our predicted values here, before we had a nice single x-axis we could look at, we do not have that in this case. We just have our predicted values, and this is 0.72618. That says, and remember, 1 is higher numbers, a 1 is a spherical that doesn't predict. So we look over here. 1 spherical doesn't predict. So this is This first one was at 0.7. So that's greater than 0.5. We would say that basically correctly classified it. If we come up here, we look at these. There's one that's 0.00009, and that says that's a near zero prediction. That works well. Spherical works well. And so that's a pretty good fit. Now here we had a misclassification where it predicted the person was bad when they were in fact good. So so that's multiple logistic regression. Let's do one more thing. We mentioned that we had some multiple collinearity because these variables correlate. And really what we should always do, and we probably should have done this first, is you must always do an intercorrelation table among your factors. I could have added age to that, but I'm just going to do everybody, including the ones with missing data, because that won't affect us here. And so, for example, KT horizontal, vertical, KT vertical, look at that 0.9 with vertical. So only one can be a winner. But when we look at, well, we don't have the other here. Let's see what happens when we do a stepwise regression with logistic regression. So we're going to, rather than enter everybody, we're going to do a forward walled test. And what that's going to do is it's just going to look at everybody, and it's going to say, as we go through, first of all, here in this first equation, this is block 0, nobody is entered in the equation. It's just straight out. And the variables that are not in the equation, do they correlate with the type of lens? Notice that every variable is significant. Everyone is significant. And if we look, we can find what's the biggest one. The greatest number on this walled statistic is a 66.581. That means sphere is the best predictor, and so step 1 is going to have sphere in it. Let's see if it does that. Oh, did I not tell it to? Variables in the equation. Okay, here we go. Sphere was picked out as number 1. Then after we adjust, I did this stepwise, but I didn't tell, oh no, here, variable's not in the equation. Okay, so if they're not in the equation, then pupil size, for example, wasn't in there, e-value. Pupil size is the next one. So if we look at step 2, after we've adjusted for sphere, pupil size is the winner. And variable's not in the equation. After step 2, we no longer have pupil size and sphere, but the biggest one next is KT horizontal. So let's look at that. Step 3, KT horizontal pops in here. And then let's go down, and after step 3, the biggest one is axial length at baseline, and so we end with that one in step 4. So notice that while everybody was significant at the beginning, after 4 steps, you no longer have variables that contribute, because vertical, e-value, and central corneal thickness were all highly correlated with the other values. So that does not mean that these are not important variables. We already established up at step 0 that they were all important. And even after step 1, they're all important. So it's a little confusing, and the reason that things fall out, or not the reason, but one effect is it's very sample dependent. So if we had done this study again, there could very well be different winners and losers. E-value may go in instead of KT vertical or something, who knows. But it requires careful interpretation, and that's why we do the correlation table that shows the correlation between these things. That it's not, that there is that multicollinearity, and we look at variables not in the equation, particularly at block 0, so that we can see that everybody is in fact a contributor. And all these chi-squares or Wald statistics are pretty high. All right, that is multiple logistic regression. Oh, wait a second. Before we do that, before we end, let's note that once we get down here, we have the final equation is sphere, KT horizontal, pupil size, and axial length. We get these coefficients. Sphere, good control. Horizontal, the higher the number, the worse it is. Or the higher number, the better it is. The greater the pupil size, the more likely they are going to be not fitting too well. Axial length is the other way. You can see the odds ratios here on how much they contribute for a unit change in these measures. You'll notice that the biggest one here is pupil size, but actually pupil size, after you control for all these other things, pupil size does become the winner. Kind of interesting. Anyway, that is multiple logistic regression.